Okay, now the question is, if this was continued forever, would we really have the entire graph of the sine function? Would we have all points of the circle represented? Well, the answer to that question is no. No way. There's no way that we have what we'd call a countable number of points that comprise all the points in the circle. The number of points in the circle is uncountable. And if you've looked a little bit about infinite sets and rational numbers, you'll understand kind of what I mean. Again, if you come back to this every year, you'll gradually see what that means. But I'm going to give you an idea. Okay, so I'm going to say we have a dense but not complete set of angles here. And all these angles, of course, are irrational because pi is an irrational number. So when we multiply a rational number by an irrational number, we have to get an irrational number. It's worth understanding how to prove that, but you might not be at that point right now. Not too difficult to prove. But it does take a little bit of mathematical sophistication. If you don't know how to do it now, you probably know how to do it in a year. In any case, it can be proven, and it's fairly easy to prove, that when you do a rational number times an irrational number, you get an irrational number. If you assume that you don't get an irrational number, you can easily arrive at a contradiction, meaning that you must have had an irrational number. Okay, well, we have a dense but not a complete set of irrational angles. What do we mean by not a complete set? It means that there are angles that we don't get. And equivalently, that on the unit circle, there are arc distances that we can't get this way. The only ones we can get, is in fact, are of the form p over 2 to the n minus 1 multiples of pi. Okay, so one example that we can't get an angle of 2 radians. Okay, 2 radians can't be constructed this way. We'll never get 2 radians. And how do we know that? Well, if we accept that this is irrational, that a rational multiple of an irrational number is always irrational, well, 2 is rational. Okay? So these are all irrational. 2 is rational. So we're never going to get 2. Okay? Is that a problem? Well, theoretically, it's something of a problem. Practically, it's not a huge problem because it's easy to prove that if we keep subdividing this, we keep getting smaller and smaller arcs, and those smaller and smaller arcs go all the way around the circle. So if we want to get 2 radians, which is probably around here, if we want to get this, we never do get it. Okay? But we get as close as we like, and actually that's probably a little too far. 2 radians is probably closer to here, but you understand what I mean. Okay? Because by making these arcs smaller and smaller and smaller and taking them all the way around the circle, we're going to get arcs that get closer and closer and closer to whatever this is, even if this is a rational number, or even if it's an irrational number that's not of this form, because there are all kinds of irrational numbers that are not of this form, okay, that don't have the form p over 2 to the minus 2 to the n minus 1 times pi. Whatever point we choose on this circle, it's either one of these points, which is really unlikely because there aren't all that many of these compared to the number of points that there really are. But whatever point we choose, we can get as close to that point with one of these as we like. And then, having gotten that, we just keep increasing n, and every time we increase n, we get points that are closer. And you can think about why that is true. So, in that sense, the points that we get by subdividing this way are what we call dense. Okay? They're dense because no matter how close you want to get to a point, you've got points of this form. Or however close you want to get to an angle, you've got angles of that form. It's dense, but it's not complete. It's not complete because Well, for one thing, you can't get any rational angles. You get rational multiples of pi, but they're all irrational. You can't get any actual rational angles. You can't get any actual rational arcs. You can't get an arc of 2. You can't get an arc of 4,097 over 523, okay? Any rational number you think of, you can't get it. And most rational numbers are not of this form anyhow, so you can't get even most rational multiples of pi. So I say this is a dense but not complete set of angles. It doesn't include any rational angles, for example. It fails to include any irrational angle that's not of this form, and there are lots of irrational numbers that are not of the form p over 2 to the n minus 1. Any number that has a denominator that's not a power of 2 isn't going to be of this form, is it? And there are plenty of numbers that have denominators that aren't powers of 2. Okay? So, in summary, what do we have? We've got the unit circle here. We get arcs of length 1 over 2 to the n minus 1 pi at step n. Okay, that's going to be the length of our smallest arc. So we can get arcs or angles, if we prefer, p over 2 to the n minus 1 pi just by counting p of the angle 1 over 2 n minus 1 pi. Now, a little theory. Rational numbers are countable. Okay? That means that we can put a counting number, we can match a counting number, 1, 2, 3, 4, 5, etc., with any rational number we want to write down. Okay? That's something you usually see in a good high school sequence. Irrational numbers are uncountable. And that's not too awful difficult to prove. It's proven in liberal arts math courses, at least in decent liberal arts math courses, which are not calculus track math courses. They're generally somewhat easier. So it's not a very difficult thing to prove that, at least at the college level, at the low level of college work. Then we can make the statement that the rational multiples of pi, well, they're irrational because irrational times pi is irrational, but they are countable because there are only countably many rational numbers, and rational multiples of pi then have to be countable. Any angle contains infinitely many angles of the form p over 2 to the n minus 1 pi in any of its neighborhoods, no matter how small. Okay, now that statement needs just a little, I've kind of built up to that statement. That means that if we're trying to get this angle here, and this isn't one of these angles, okay, if it's not an angle of the form p over 2 to the n minus 1 pi, we're never going to hit it. But, now by a neighborhood of that angle, I just mean an angle between something a little bit on this side and something a little bit on this side of the angle. Something a little bigger, something a little smaller to something a little bigger. An angle a little smaller than this angle to an angle a little bigger. No matter how little is, there are going to be infinitely many of these angles between a little bit less and a little bit more. Okay? And by a range of angles, it goes from a little bit less to a little bit more. That's really what I mean by a neighborhood. There's a more formal definition of neighborhood, and you'll see it eventually if you continue in mathematics, to get a good, at least general working knowledge of the general field. So there's a more formal definition of neighborhood, but if you understand what I mean any neighborhood, no matter how small. Again, that means a little bit less to a little bit more than whatever this angle is you're trying to get close to. There are going to be infinitely many angles, no matter how little is. No matter how tightly you squeeze the interval around this angle, there are going to be infinitely many of these. Okay? And that's really what we mean by a dense set. Now, we go on, and just to give you a preview, we do what we call a topological completion of the point. So if we imagine that we've done this, and it's been done for infinitely many subdivisions, okay, then we're going to get something that doesn't have really any spaces between the points, but there's still spaces between the points, and that's contradictory. And you have to understand infinite sets a little bit to understand how that could be. Interesting topological idea. But then you say, okay, any of the numbers that we haven't got here, we're just going to say, well, if you got this number here, that value is going to be whatever number doesn't ever get far from any of these other numbers, okay? And I don't have a much better way to say that, so I'm going to kind of stop there. But we do what's called a topological completion. We just fill in the holes, even when there aren't any holes, and we get the complete graph, which is kind of mathematically interesting, but that's probably down the road a little bit. Something to think about, though, and again, this is worth coming back to about once a year, so that you have a point of reference for things that you're going to be looking at in your mathematics curriculum.